The first speaker is Yoshinaga Misako from Osaka University. And the title is Edelman-Reiner Conjecture Revisited.
Other organizers also thank for coming for conference. So I'm talking about Edelman-Reiner conjecture. It is actually normal conjecture because it is has been solved about 20 years ago. But still, I think it is really source of maybe interesting. So I'd like to kind of survey what has been going last 20 years about Reiner conjecture. So let's start with what is a conjecture? Okay, so here, so in this space, there are several notations which will be introduced later, but anyway, phi so let's phi be a system in the Euclidean space with exponents E1 to EL and constant number is denoted by H. And for any root alpha, so alpha can be considered as a linear form of the vector space. So we can define the hyperplane, affine hyperplane defined by alpha is equal to HK. So this is denoted by H alpha K. And we collect this kind of hyperplane. We define two kinds of affine hyperplane arrangements. So one is the so-called extended Catalan arrangement of the system phi and some parameter m, which is the collection of H alpha K, the affine hyperplane, where alpha runs all positive roots and K runs all integers from -m to +m. So this is one of small example coming from B2 root system. So for each hyperplane, we arrange several parallel hyperplanes. Sorry. And we also define C arrangement similarly, but I think so what is a conjecture? Conjecture is about the freeness of the cone of these arrangements. So I will explain what is cone, but the conjecture states that the cone of the Catalan, M extended to Catalan arrangement is free with exponents 1, E1 plus MH, blah, 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 EL plus MH. And similarly, cone of C arrangements is also free with some exponents described by the Fisherman graph. This conjecture has several combinatorial corollary by the Peirot's factorization theorem. These exponent and freeness concludes the characteristic polynomial of this Catalan arrangement factored into like this. And the number of chambers in the Catalan arrangement is described like this. And actually, that naming Catalan comes from the number of chambers in the five form of Catalan arrangement. Like L minus 1 increases M equals 1 becomes the Catalan number. And we also have similar formula here. Okay, so this is the conjecture. So I guess originally this conjecture is considered in the context of combinatorics of Catalan arrangements. By the way, so this Catalan comes from some paper, one of the papers of some of the audience, I guess. Nathan Williams. Christian. So here, there is Catalan. and Edelman lifetime of the so in the first part of this talk, I'd like to give how to prove this one. And to prove this one, other kind of mathematics is very crucial to this making all primitive words or black Actually, this theory, in the proof of the Edelman-Reiner conjecture, some notions are very crucial, striking applications to Edelman. So, in the first part of this talk, I'm talking about this, how to apply these things, Edelman-Reiner conjecture. So this is one part of I'm talking. But this solution is not really explicit. So, so we can actually prove the freeness of the Catalan arrangement, but Catalan C arrangement. But still, there are many things to be clarified. For example, we didn't know the explicit basis of the free arrangements like this. And one of the possible study was, for example, we have several very explicit formula, combinatorial formulas about characteristic polynomials and chain class. This can be related to the lattice points theory, Treyer theory. In the second part of this talk, I'm talking about lattice points counting methods are very useful to conclude the combinatorial assertions of the Edelman-Reiner. So this was first done by Alice for the characteristic polynomial of the Catalan arrangements. And later, I gave some refinement for C arrangement. This is the second part. In the third part, another thing comes, quantum integrable systems. So in 2016, Misha Feigin told me that this part is really closely related to the one of the notions, the so-called quasi-invariant quantum integrable systems. And so recently I'm working in connection with this notion. So I'm talking about these things in the third part of the talk. Okay, so this is the last round of this talk. Okay, so let's start the first part. The key notion is the free arrangement. So it was already defined by the study, but I just repeat for my talk. Okay, so let A be a central hyperplane. So it is the collection of hyperplane which has polynomial. Here S denotes the polynomial over X1 to XL. So we suppose X1 to XL are the real basis of this vector space. We denote del S the modules of derivations. So here we consider this as the module of a kind of differential operators. So in arrangement A, we define B of the set of derivations delta, which satisfies. So delta is a differential operator, so we can apply this to the polynomial, particularly this linear of alpha I. Then the required condition is the resulting polynomial should be divided by alpha I. So this should be should hold for any I from 1. So the set of such delta is called the modulo of logarithmic derivations and denoted by d of h, d of a.
The arrangement A is called free with the exponents D1 to L. So this module free is basis delta 1 to delta 8 is described
degrees. So where degree delta I counts the degree of this coefficients of homogeneous spaces. So this here is a very small example. So this is like B2 reflection arrangement defined by x, y, x minus y, x plus y equal to 0. And then these two vector fields delta 1 and delta 2 form the basis of this module. So exponents are masked.
And then, so if we know the freeness, so freeness concludes several combinatorial properties of the arrangement. So the first one is
The so-called Terrao's factorization theorem. So if we know A is free with the exponents then one of the most important invariants of the arrangement, the characteristic is the product of exponents. By the result of the Slavsky's formula, we can also count the number of chambers to exponent. Okay, so let's go to the Catalan C arrangement. So as I defined,
the Catalan C arrangements are defined for
reducible root system.
but here we
To discuss the freeness of these arrangements, we have to consider the cone, taking the cone of the Catalan arrangement. So
here we define
H tilde to be the points, the set of points xg in one-dimensional higher space defined by alpha x is equal to theta. So this is the cone of the phi hyperplane defined by alpha x is equal to theta. Then the cone of the Catalan arrangement is the collection of this kind of hyperplanes plus one more hyperplane denoted by
H0, sometimes called the hyperplane of A. We define frequency for C arrangements.
Then the Edelman-Reiner conjecture
Is the precise, again, the Edelman-Reiner conjecture states that the cone, this is a central arrangement in L plus 1 dimensional space, is free with this described exponents. So C arrangement space also. Okay, so the conjecture states the freeness of this Catalan C arrangement. But for simplicity, from now, we just discuss what Catalan. Now we are going to talk about the proof of the freeness of
the cone of the Catalan arrangement.
So as I said, we start from this kind of affine arrangement, the Catalan arrangement. And we take the cone, so homogenization. So the conjecture states this in. But to the proof, the most important, the very crucial thing is this arrangement. The hyperplane of the say H0 or
The hyperplane defined by G is 0. Then we have a natural, so this A5 is nothing but the reflective hyperplane arrangement. But this restriction naturally has the multiplicity coming from the number of parallel hyperplanes. And in the proof of the conjecture, so freeness of this restricted multi-line is the most important step. So here, so let's define the module of logarithmic derivation with multiplicity in m plus 1 will be the set of derivations which satisfies. If we apply the operator to alpha h, then it is divisible by not only alpha, but also minus alpha h. So we are looking at so in the proof, so the freeness of this module is the most crucial point. This is we are actually related to the side of notion of Hodge field relation. But before that, let's see some small example of such this kind of multi-line. So here, so this is like A2 line. We have the basis delta mark to this. If we put the multiplicity into 3, then the it is not very easy to find the logarithm.
You mean 1, 2 there?
Correct?
Exponents are 1, 2, or 1, 3.
You are right. Sorry. Yeah, this is typo. 1, 2. 1, 2 is 2. Thank you. 1, 2, and here 4, 5, 6. Yeah, we have a bit complicated, but we have this kind of basis for this. One of the observations is just simple. So this is the original one has exponents 1, 2, but the multiplicity one has exponents 4, 5. And this is obtained by shifting the Foxter number. So in this case, the Foxter number. So this shifting by Foxter number appears in many ways. Yeah.
Would it look differently because you've chosen it, not to actually be the root hyperplanes? You've like made it. Would that make the form of the delta primes like more guessable if you?
Okay, so you mean that if you change the gradient?
Yeah, like the lines aren't actually the root hyperplanes. You've
So three lines cases they are similar.
They're similar.
Yeah, if we consider fourth line, then it becomes very difficult, much more difficult. Actually the exponents are depending on the gradient of fourth. Yeah, very complicated. Thank you for asking. Okay, so before introduce primitive derivations, let's see very quick where these notions comes from. So it comes from so this is a very quick view of Professor Tori Saito's theory. So here we start from simple singularity. So this is basically surface singularity, which has isolated simple singularity of type A. And this singular surface can be embedded into some of the so-called universal unfold. So this is a kind of deformation of the singularity on the parameter space C level. And then so far this is theory singularity. Singularity theory. But for type E-type singularity, it is known to be able to realize this kind of thing purely theoretical way, the so-called Briscoe Sloterdijk theory. So actually, this deformation space, total space, it can be embedded into the AD type Lie algebra as the affine space, which is transversal space to the subregular important form. And this map is considered as the restriction of the adjoint quotient map, which maps to Originally it is J over G, but it is equivalent to H over cut down by the Shiba X displacement. So this kind of, in this theory, one of the important point is to study the Gauss-Manning connection of this family. So it is, very roughly speaking, studying of differential equations of the change of fiber. So it is formulated as the kind of connections, the so-called Gauss-Manning connection. So as I said, these things are purely formulated in purely theoretical way. So these notions are also interpreted in theoretical way. And actually, he formulated these, reformulated these things purely in terms of this kind of invariant theory representation. So, yes, now let's see the connection. So here, instead of the Gauss-Manning connection with fiber, we consider very simply minded. Delta 1 to delta 2 maps to like this. Question. Yeah.
I'm sorry, just so when you describe the Gauss-Manning connection, what is R square?
So it looks like it looks the second cohomology fiber.
Thank you. Thank you.
So it is the dimension of the Milnor fiber.
In your formulation, you need to add more pole, singular locus. Yeah, I'm afraid something wrong. But it's not essential, so I don't want to go into this.
You mean here?
Yes.
Yeah. So this part should be modified by logarithmic modulo logarithmic. Okay, so yeah, some equivalent to the Gauss-Manning connection is actually in our coordinates formulated like this. Just differentiate the coordinate function by the multi-vector field. Then the one of the crucial notion primitive derivation is primitive differential vector fields, even explicitly even by 1/2 times this kind of differential field. So then now we formulate the crucial theory which is also important for the proof of Edelman-Reiner conjecture here. So this primitive derivation, which looks very strange object, but it connects the module of logarithmic derivation to multiplicity of type 1. Then this lambda D action gives the isomorphism of vector spaces of the module of logarithmic derivation is multiplicity to m plus 1 to m minus. So this gives the correspondence between these two different parts. And actually this helps to prove the freeness of this one, because we know the freeness of multiplicity to m minus 1, then using this map we can prove up the basis of this one to m plus 1. And actually this is the proof of freeness. So this is what I said. So the module. So here we discussed with W invariant path, but actually this means for the logarithm derivation, but basically M plus 1 for Y. And the exponents is like this aspect. Yeah, so basically, this is, as I said, this is the very crucial part of the Edelman line of conjecture. So we know, again this diagram, but we know now we know the freeness of this one using the cycle primitive derivation. And then we can lift the basis, somehow. Then you know, so this is the stage of the proof of the Edelman line of conjecture. And these notions are recently actively studied by many other people. For example, one of the directions of generalizations towards the unitary pictures of these constructions. So this is the first part of this talk. Now let's go to the second part, the relationship. That is what. So here, the crucial notion is so-called characteristic one polynomial. So let's start with some very explicit example. So start from just 3 lines defined by y is 3 times x, y is twice of x, y is 0. So these are 3 lines. The problem is counting the number of points of modulo q complement. So this means if we fix positive integer q, then we can consider these equations on the modulo q was so q over q, z over q. So we want to count the number of points in z over q square removed these 3 lines or something, some subset. And the resulting number is not very easy. Actually, the number becomes q square minus 3q plus 2. Then, so if q is equal to q is congruent to 1 or 5 modulo 6. But sometimes it becomes q square minus 3q plus 3 if q is congruent to 2 or 4 modulo 6. But in other case, it becomes also q square minus 3q plus 4 if q is congruent to 3 modulo 6. Furthermore, the number can be q square minus 3q plus 5 if q is divided by 6. So this looks a bit complicated, but this kind of description of the functions, the so-called quasi-polynomial. So it is not just the polynomial, but some polynomials. So described by some polynomials depending on variables. So for hyperplane arrangement, this kind of description is true for any hyperplane arrangement. So this was introduced by Kamiya in 2007. So the result is for any hyperplane arrangements defined over D, like this example, there exists some positive integer rho, the so-called period, and some polynomials f1 to f rho, so period many polynomials, such that the modulo q complement, say d over q, d to power l minus the union of subsets defined by like hyperplanes. So the cardinality becomes like this. So it is sometimes f1 of q, but if q is equal to 1, modulo rho. So, well, I don't want to share too much, but this is, if A is not central, then this description is true only for sufficiently large Q. But anyway, so this kind of description is the so-called characteristic quasi-polynomial. And there are some several more nice properties of these things. They, so here, by definition, we say there are low polynomials, but many of these polynomials are coincident. Actually, if I and J has the common GCD with row, so GCD of row and I is equal to GCD of row and J, then I's polynomial, sometimes called the constituent, is equal to J's constituent. So, so this can be observed. This is also observed here. So one first constituent, biggest constituents are equal. That's because 1 and 5 are prime to 6. Blah, blah, blah. And another important thing is the prime constituent, F1 or some other constituent prime, so is equal to the characteristic polynomial into 7. So this characteristic quasi-polynomial is a kind of refined notion of the characteristic polynomial. So another important thing is not only first constituent, other constituents are also make sense polynomial. So, for example, the final constituent, so which corresponds to the Q divided by the period rho, is nothing but the characteristic polynomial of toric arrangements defined by this original hyperplane arrangement. I don't go to in detail the toric changes. Anyway, here I would like to tell you about the a kind of equation, functional equation. First proved by Asanosadis for characteristic polynomials and later by myself characteristic other polynomials. So anyway, the formula says the characteristic polynomial or characteristic polynomial of nth pattern arrangement is nothing but that of original Fock-Star while arrangement of Q minus n. So the characteristic polynomial or quasi-polynomial of pattern arrangement is obtained from the original characteristic polynomial by just shifting the parameter by MH. I briefly sketch how to prove this formula. So the proof is purely combinatorics of lattice points. So the idea is to identify d over 2d, d over 2d to L. So in this case, after here, we just consider iterate is just the grid. The lattice points 1 to 2 minus 1 to 2, like this. And we also want to use the so-called Earhart quasi-polynomial of some polytope. So here, polytope P defined by so in A2 case, the polytope P defined by these include states is greater y equal to 0, y is greater y equal to 0, and x plus y is up to 1. So this is this unit sequence is that. And we consider the Earhart one, in this case, Earhart polynomial, this one, namely LP of 2 is the number of lattice points on the Q times expansion of P. Okay, phi this kind of Yarharsh polynomial is related to characteristic plus polynomial. So we consider, so as I said, we consider by definition, the characteristic quasi-polynomial counts the number of points in this space. But we can identify this space with this 1 to 2. Then we have to remove some subset coming from hyperplanes here. So hyperplanes here is defined by x is equal to 0, y is equal to 0, and x plus y equal to 0. But x plus y equal to 0 should be interpreted as x plus y should be multiple of q. So this means we remove y is equal to 0 here, x is equal to 0 here, and x plus 1, x plus y is equal to here, this diagonal orange line. Then the remaining part is nothing but the union of two weak simplex. Actually, this is the multiple of Q minus Coxeter number. And then if we compare this with that of Catalan arrangements, so in this case, we have to remove more hyperplanes coming from Q, y is equal to minus 1 here, y is equal to plus 1 here, and x is equal to minus 1, plus 1, and some diagonal. Then the remaining part is again the union of two simplices. But the sign becomes smaller. And the size of simplex becomes smaller is exactly controlled by the Coxeter. So in this case, the characteristic quasi-polynomial is nothing but twice means there are two simplices. Twice of the Yarharsh polynomial of Q minus H. The size of the simplex are Q minus H. And here Q minus 2H. So this is the reason why this shift by Coxeter number. And so this is just an explanation for type A2 system, but this can be generalized to any root system using the coordinates of the root system. Okay, so this is the second part. Now let's go to the third part, the influenced by quantum integral systems. Okay, so as I said, one of the crucial point of the proof in the Edelman-Liner conjecture is that this isomorphism of between the module of logarithmic derivations of W invariant part to that with multiplicity 2n plus 1 induced by the inverse of primitive derivation delta. And we shall point it out this kind of this is essentially equivalent to the things which is called M quasi-invariant in the quantum integral system. So I'm not going to talk about these things in detail, but how this can be interpreted. So I'm explaining how the results, some of the results in this fields can be interpreted in our context. So anyway, so what is M quasi-invariant? So M quasi-invariant is the subset of polynomials. So the set of F polynomials, it satisfies if we apply the reflection to F, 1 minus the reflection to this polynomial, then it is tried to find alpha, the root of 2n plus 1. Yeah, so this is this clearly looks like the definition of the modular of logarithmic derivations with multiplicity to m plus 1. And actually, this was explained by this next proposition. So for any W invariant derivation vector field delta, it is contained in n plus 1 multiplicity module, if and only if so one of the coefficients is contained in this class.
You mean Fi?
Sorry,
F1. F1, Fi.
One of them or all of them?
yeah,
All of them.
all of them.
Yeah.
So by the assumption of invariance, so if one of them satisfies this now, then other ones.
Okay.
Okay, so as I said, there are several results in the quantum in the context of quantum integral system. One of the very interesting result is the integral expression of the basis of this space of quasi-invariant. So it is studied, originally studied by Taylor and Veselov and Bandro and Mujica, and the following was so to be honest, I do not know much about the original studies, but Misha kindly interpreted for us as follows. So this is basically the type A system case. So let G be the polynomial of T, actually T is x1, other variable x1, so this should be XL. Okay. The product of T minus x1 to T minus xl. And we define some derivation eta and k, the vector field eta and k by the sum of something times di, where I runs from 1 to L, where the coefficient is an integral from 0 to xy of the polynomial t to k. Then together we give some very trivial data should be always complete. These new vector fields which have the integral expression form a basis of this module. Actually, so these are W invariant vector fields. So it is contained in W invariant, but actually the basis of this module of logarithmic derivation with multiple m plus 1. So this is a kind of very strange applied because in this theory that we know this map is this theoretical, but the map is very difficult to describe in general. So I was surprised that in quantum integral system, people knows very explicit basis of this model. Very wonderful. I think that most of simplest non-trivial case. So because the A1, then L is equal to 2, and M is equal to 1, and K is equal to 0. Then we have the vector field of eta 1, 0, and the sum of here should be 2, the sum of I is equal to 1 and 2, where this coefficient is nothing but the integral of t minus x1 to times t minus x2 from 0 to x time. Then if we apply the vector field to one of the linear form x1 minus x2, then by this form, by the definition, the result is just the integral from x1 to x2 of this point. And it is x2 minus x1 というのがdivide, so clearly divided by x1 minus x2 cube. So I know this formula for a long time since high school. But I was surprised because this formula gives the condition that this vector field is contained in non-trivial vector fields of multiplicity 3. One more very important thing with this integral expression is very well consistent with the actions of primitive derivations. Say, if we apply primitive derivation nabla d to one of this one, then just this m shifts decrease up to some constant count. So, in some sense, this integral expression gives the very explicit basis of this nabla d inverse action. Yeah, please.
Excuse me. Go back to the previous slide for
Yeah.
a second. Are you able to say or what it would be in general? This looks special to type A, but there's some other way to get G in general.
So it is still ongoing project, but we have at least type B case we have.
Oh, okay, so it's still ongoing.
Yeah. My students. But it is not general, we don't know how to describe this kind of thing or any
X78.
Okay, now let's go back with Catalan language. So far we are looking at the definition for the multi-element. But we also want to know the explicit basis for the Catalan arrangement itself, not the arrangement, multi-arrangement. So it can be done by using a kind of discretization of the integral formula. Actually, let's define, let's delta, so this triangle delta is just the difference of delta like this. And we formulate the discrete integral using this formula. Say, for any function f, if you have a indefinite of discrete integral, capital F. So if you find some capital F satisfying these properties, then define the discrete integral from A to B of this small f as the capital F of B minus A. So this is a kind of discrete version of the integration. Then just to change the integral to discrete integral. So let us define eta tilde mk to be the sum of these discrete integral times. Yeah. So we have some discrete analog. Yeah, one of the small new thing is here original integral expression we consider mth power of polynomial g, but here we have to consider the so-called falling power. So g of m underbar is gt times gt minus 1 times blah 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 gt minus x. Okay, so we introduced some analog, discrete analog. So as I said, just the difference is we replace integration by discrete integral. Power is replaced by volume. Then these give the very explicit basis for the logarithmic, the modular log derivation to Catalan language. So very roughly speaking, this result shows Catalan arrangement may be considered as a
kind of discretization. Multi-arrangement. So this is Chattanooga arrangement. As I said, as we saw, so related to the Edelman-Liner conjecture, we first consider the cone homogenization here. Then restriction to the hyperplane. Then we have a natural multi-arrangement. And the composition of these two arrows is a kind of taking leading down, because here we have some homogenization, taking the zero. Then this is a kind of taking leading of the final object. Then, as we saw, so here we have the basis for integral expression of the very nice integral expression of the basis. And a kind of discretization of this integral expression gives that basis for the Chattanooga arrangement, a fine arrangement. So natural question is, so this is also work in progress. Can we discretize the primitive derivation? I mean, so here primitive derivation acts on this multi-arrangement of W invariant part, like multiplicity to M plus 1 to M minus 1. And here we have a kind of maps, leading term maps. Then, naturally, we may ask, are there any natural extension or discretization of this one? So, again, this is possible, at least for type A. So let's, but we have to introduce another difference operator, plus minus. So here, delta I plus minus is f of x plus ei. So ei is this standard basis. But here x is f by x minus x. So f1 plus ei minus f1 of x minus ei divided by 2. Division by 2 is not very important. So we have this is a kind of difference operator. Then using this difference operator, we can define the tilde rational difference operator like 1 over this product of differences times determinant of blah 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 and the difference operator. So assuming we recently obtained is available is for type A case, this gives a good candidate for this. So actually, this operator acts on the W invariant part of it. Fine, M extended to Chattanooga arrangement to that of M minus multiplicity M minus 1, which commutes this diagram.
I mean, but of course, that looks like it generalizes. You just divide out by the any polynomial. You would have tried that for the other types.
Yeah. A bit more.
Okay.
Yeah, so this is a kind of summary of this talk. So we start from Chattanooga arrangement. Taking the cone restriction to the hyperplane at infinity. So we have a multi-arrangement here. So the rough idea, so as I said, the Edelman-Liner conjecture says this is free, and it is now true. But the important thing with the primitive derivation is defined on this space. And some recent results seems to suggest the Chattanooga arrangement itself can be considered as a kind of discretization of this multi-arrangement. So this is what we are going to do with collaborators. So actually,
for example, about the level of basis, you have a integral expression like this for type A. And this, if you discretize this integral formula very simply, then this would not okay. But this procedure works only for type A. Even there are some integral expression other than type A case, this is not this doesn't work. This. On the other hand, there is a yeah, so I think this is just hard suggest. This is a kind of general formula for limited derivation. And type A, actually type A and B and D case, we can simply discretize this formula by replacing partial derivatives by this difference operator. Then this works for making this diagram convex. So, as I said, these are a kind of very ad hoc computations at this moment. For type A case, everything goes very well. And for other cases, it depends on the object. So, for example, this replacement of primitive derivation by discrete primitive derivation works at this moment only for type A and B and D. Strangely, type C is not good for us. It is one of the ongoing projects with Abe and Enomoto. And also,
And the map is isomorphism. On the left, you have isomorphism.
this part. Yeah, isomorphism. Yes, yeah, you're right. Yeah, that's true. Yes, so this is isomorphism and
Isomorphism with respect to which structure?
for simplicity as vector space. But of course, isomorphism has a polynomial ring over P1 to PL minus. I mean, other than PL.
You don't consider difference operator? But maybe we can discuss it.
Yeah, and another ongoing project in Nisha and one of my students is the integral expression can be expanded more, not only type A, but B and some of those complex features. Maybe, yeah, maybe it's related to some consensus question. One of the, I have no clear idea, but one of the possible future directions is discretize the structures. Yeah, in this part to somehow to shut down. That's all. Thank you very much.